Welcome to the third lecture of the course. So, in the last lecture we have talked about free vibration of undamped single degree of freedom system. In this lecture we will add damping to the system and see how we can obtain the damped free vibration of single degree of freedom system and solve the different aspects of damped free vibration of single degree of freedom system and analyze them. Okay. So, let us start with again a simple spring mass system, the same system that we have been considering. So, only difference that we do is we add a dampers to this system. So, we add a damper to the system. So, we add a damper C to the system. So, what does this damper do? So, this damper is also this figure is also sometimes called a dashpot. This is how conventionally we represent pictorially a damper. Okay. So, this is also often called a dashpot. This is called a spring. Okay. So, what does this damper or dashpot does to the system? It actually adds a damping force or a dissipative force to the system. Okay. So, it will always add a dissipative or damping force to the system. This kind of system where there is a damper, the energy is dissipated or taken out from the system. So, the energy, unlike the previous system when there was no damping, is no longer conserved. The energy is withdrawn or dissipated from the system because of this damping. So, there are various models of damping. We will talk about them later in the lecture, but let us start with the most simplest form of damping, which is linear viscous damping. Okay. So, what do we do in linear viscous damping? We say that the damping force is linearly proportional to the velocity of the system. So, Fd is some constant c into the velocity of the system, which is u dot, where this c is called the coefficient of viscous damping, or more commonly as the damping coefficient. Okay. So, therefore, when we try to draw the free body diagram of a damped single degree of freedom system, apart from the inertial force and the spring force, we need to add the damping force, which is Fd equal to c into u dot. So, this is the new part that is coming into the equation from now on, and therefore, we will see how to analyze this new form. Okay. So, if we write down the equation of motion from this free body diagram, we just get an additional term c u dot in the equation of motion, and it becomes m u double dot plus c u dot plus k u. So, like previous case, let me just write it in a different form. Let me just write this as c by m into u dot plus k by m into u equals to 0. Okay. So, this again I am going to try to write as u double dot plus 2 zeta omega n into u dot plus omega n square into u equals to 0. We already know that omega n square is nothing but k by m, and it is the natural frequency of the system. What we do here is that we write c by m, that is the damping coefficient by the mass, as some 2 zeta into the natural frequency omega n. So, this zeta is called the damping factor, or sometimes some people call it as the damping ratio, either damping factor or damping ratio. Okay. So, this zeta is a fractional value, it always lies between 0 to 1. Okay. So, now what we do is we try to solve the system. We try to solve the system and try to get the free vibration response of the system. So, let us go into the next slide and try to find out. Let us see how to find out the response of the system under damped condition. So, similar to the previous case, here also we will assume the solution as ut equals to e to the power lambda t, okay, and try to solve the equation. So, we have this equation of u double dot plus 2 zeta omega n into u dot plus omega n square into u equals to 0. Okay. So, we then put this assumed solution into this equation. So, if we do this, we are going to get it as lambda square into e to the power lambda t plus lambda into 2 zeta omega n into e to the power lambda t plus omega n square into e to the power lambda t is equal to 0. Okay. So, again e to the power lambda t cannot be equal to 0. So, from this equation we can write as lambda square plus lambda into 2 zeta omega n plus omega n square is equal to 0. So, this is a simple quadratic equation. So, we can get the roots for lambda. So, the roots for lambda is going to be minus zeta omega n into plus minus omega n square root of zeta square minus 1. Okay. So, these are the two roots of the solution. So, once we get the two roots, we can always write the response. So, since this is a second order differential equation, we will have therefore, we have two roots and therefore, we have two unknown constants that we have to solve for. So, therefore, we write this as C1 into e to the power minus zeta omega n, okay, zeta omega n plus omega n zeta square minus 1 into t plus C2 into e to the power minus zeta omega n minus omega n into zeta square minus 1 into t. So, I can further simplify this and write this as minus zeta omega n t into C1 e to the power omega n zeta square minus 1 into t plus C2 into e to the power minus omega n zeta square minus 1 into t. So, this is the response of the system. Of course, we have to find out C1 and C2. Now comes the question that zeta square is whether zeta square, so three cases can happen, that zeta could be less than 1, zeta could be equal to 1, zeta could be equal to 1 and zeta could be greater than 1. So, for each of these three cases, the nature of though the expression of the solution is going to remain same, but the nature of the solution, the physics of the solution is going to change depending whether zeta equals less than 1, equal to 1 or greater than 1. Okay. You can realize when zeta is less than 1, this part is going to be an imaginary part, because zeta square is less than 1. So, we have square root of a negative term. So, it will become imaginary, whereas so will not be the case when zeta is greater than 1. So, for a damped vibration problem, we solve 3 cases for the 3 conditions of zeta, and these cases are called under damped system, a critically damped system and an over damped system respectively. Okay. So, now we will individually look into all of these 3 cases and solve and analyze the problem for each of these 3 cases. Okay. So, let me get into the next slide. So, let us talk about the under damped system when zeta is less than 1. So, when zeta is less than 1, I will have my lambda as minus zeta omega n plus minus omega n. Now, zeta square minus 1, because zeta is less than 1, because zeta is less than 1 is going to be a negative number. So, this should be written as I, where I stands for root over of minus 1 into 1 minus zeta square. Okay. So, let me even further simplify this and write this as minus zeta into omega n plus minus I into omega d, where omega d is nothing but the replacement for omega n by 1 minus zeta square. Okay. So, now let us write down the response of the system. So, the response of the system is now going to be e to the power minus zeta omega n t. I have already solved in the last slide, e to the power minus zeta omega n t into C1, okay, e to the power I omega d t plus C2 into e to the power minus I omega d t. Okay. So, this can further be expanded and written as e to the power zeta omega n t into C1 plus C2 into cos omega d t plus I C1 minus C2 sin omega d t. Okay. Right. So, now again similar to the free vibration problem, I can solve for C1 and C2 based on my initial conditions. So, let me assume the initial condition to be the same as that. So, let us write down the initial condition. It is exactly same as that of the free vibration undamped case, where u t at t equal to 0 is u 0 and u dot t at t equals to 0 is equal to u dot 0, right. So, this is my initial displacement, this is my initial velocity. So, this two initial condition can be applied to this expression and we can solve for C1 and C2. So, let us try to do this. So, let us see what is u0. So, u0 is going to be only C1 plus C2 and that is going to be u0. Okay. And then what is u dot 0? So, let us find out first u dot t. U dot t is going to be minus zeta omega n e to the power minus zeta omega n t. I am just differentiating this expression, nothing other than that. So, C1 plus C2 into cos omega d t plus I C1 minus C2 into sin omega d t, okay, plus e to the power minus zeta omega n t into I have minus omega d C1 plus C2 into sin omega d t plus I omega t C1 minus C2 into cos omega t. Therefore, u dot 0, which is going to be u dot 0 is going to be, so I have to put t equals to 0 here. So, if I put t equals to 0, I will have minus zeta omega n C1 plus C2, and then I will have plus I omega d C1 minus C2 is equal to u dot 0. Okay. So, C1 plus C2 I know that is equal to u0. So, if C1 plus C2 equals to u0, then I into C1 minus C2 can actually be obtained as u0 plus u0 into zeta omega n plus u dot 0 by omega d. Okay. So, this is going to be the expression for IC1t. Okay. So, if we plug in this value and this value into this expression, we can get the expression for ut in terms of the initial condition. So, let me do that. Okay. So, if I do that, I am going to get ut as e to the power minus zeta omega n t into u0 cos omega d t plus u dot 0 plus zeta omega n u0 by omega d into sin omega d t. Okay. So, this is what we are going to get when we plug the initial condition into this expression. Now, let us carefully look into this expression of response. We see that this can again be written as e to the power minus zeta omega n t into some a, which is the amplitude, which is going to be u0 square plus this square root of that. It can always be written as cos omega d t minus some phase angle phi. Okay. So, this can always be written in this form. Okay. So, now what do we understand from this expression? We understand that for an underdamped case, the free vibration of a single degree of freedom is going to be a cosine function or a sinusoidal function. This is going to be a sinusoidal function multiplied by an exponentially decaying function. Therefore, what do we get as the response? We get a sinusoid, but with a decay of e to the power minus omega n t. So, this is the response that we are going to get. So, this is my response, underdamped response of a single degree of freedom system. So, this is time, this is displacement. Okay. So, the amplitude is going to decay in an exponential form, and if I draw the envelope of the decaying amplitude, that is this line is going to have an expression of minus zeta omega n t. Okay. As well as this line is going to have an expression of minus zeta omega n t. Okay. So, this is what we get from the response of an underdamped system. And then if you look further into it, the time period of the response, okay, is no longer going to be T n, that is 2 pi by omega n, but rather this is going to be T d, which is 2 pi by omega d, where omega d is nothing but omega n into 1 minus zeta square, and this omega d is called the damped natural frequency. Damped natural frequency. So, let me just summarize once more. So, if we have a single degree of freedom undergoing free vibration due to initial condition and the damping factor is less than 1, then the response of the system is going to be sinusoidal with a time period of t 2 pi by omega d, where omega d is called the damped natural frequency, which is slightly lower than omega n, and the amplitude of the response of this sinusoid is going to decay exponentially, and the decay is expressed by e to the power minus zeta omega n t. Okay. So, therefore, I hope that the underdamped system is understood well. Let us now move into the critically damped case. So, let us now go to the second case, which is the critically damped case, okay, where my zeta is equal to 1. So, let us now look into the second case where zeta is equal to 1. So, when zeta is equal to 1, let us see what is happening to lambda. So, lambda is minus zeta omega n into plus minus omega n into zeta square minus 1. So, since zeta is equal to 1, we go to the case where the quadratic equation has only one single root. So, this part actually goes to 0. So, I have a single root for lambda, which is minus zeta omega n. Okay. So, but the governing differential equation is still a second order equation, though there should be two unknowns in the solution of this second order differential equation. So, how are we going to deal with that? So, if you look into the solution of ordinary differential equation, you will see that the solution in this particular case is going to be e to the power zeta omega n t into C1 plus C2 into t. Okay. C1 and C2 are the two unknown constants which we have to find out from the initial condition. So, these two are unknowns which we are going to find out from, we need to find this out from the initial condition in the exactly same way that we did from the last case where zeta was less than 1. Okay. So, now let us see how this response is going to look like. So, what is going to happen in this particular case is that since there is no oscillatory motion, since there is no I omega e to the power minus I omega n t part, this response is not going to be oscillatory at all. Okay. So, the response of this, if this is the time and this is the displacement, okay, the response is not going to be oscillatory, is just going to decay down exponentially. Okay. I will show a better plot in the later part of the lecture. Okay. So, this is a very ideal case where the oscillator, so this is the minimum amount of damping required to stop the oscillatory motion of a system completely. Okay. So, let us get into the third case which is called the overdamped case where zeta is greater than 1. So, this is zeta is greater than 1. So, let us look into the solution of the system or the response of the system when zeta is equal to 1. So, let us go back to the same old lambda. So, lambda again is zeta into omega n plus minus omega n into zeta square minus 1. Okay. So, zeta square is zeta is greater than 1. So, this part is no longer negative. So, there is no imaginary part into this. So, therefore, the response is going to be ut is going to be e to the power minus zeta omega n t into C1 into e to the power omega n zeta square minus 1 plus C2 into e to the power omega n into zeta square minus 1, okay, into t into t. Okay. So, this is no longer negative. So, I do not have any imaginary part here. So, the response is going to be completely non-oscillatory. Okay. So, let us look into how the response is going to look like. Okay. So, this is a plot which shows the response of the system for various damping condition. Okay. So, we have an oscillatory motion. So, this is for under damped system. So, I have drawn this particularly for a particular value of zeta equals to 0.05. So, it is oscillatory with a decreasing amplitude. This red line is the critically damped case where zeta is equal to 1. Okay. We can see there is absolutely no oscillation, and this dotted green line is the over damped case where zeta is greater than 1, and for this particular case I have drawn it with zeta as 1.2. Okay. So, you will see as zeta increases over 1, the rate with which the response decays actually becomes slower and slower. Okay. It becomes slower and slower. So, this is if zeta increases, the slope with which the response decays actually becomes slower and slower. So, therefore, critically damped system or zeta equals to 1 has the fastest rate of decay. Okay. And as zeta increases for an overdamped system, the rate of decay of amplitude decreases, and therefore, critical damping is the minimum damping required to stop the oscillatory motion and to obtain the fastest rate of decay. Okay. So, let me just talk quickly about the various about the various values of damping that the real life engineering material and structures experiences in reality. Okay. So, the value of zeta or the damping factor is usually very small for the common engineering material that we encounter. You can see for metals it is less than 0.01. Okay. So, it is less than actually 10% of damping. Okay. And for rubber it is almost the highest, and it is around 0.05. Okay. Whereas, for reinforced concrete structure it lies somewhere between 0.04 to 0.07. But there is other thing that I want to highlight from this slide, that is that damping not only depend on the material that we use, of course it depends on the material, it will be more for metals, it will be less for metals, more for concrete, more for rubber, but it also depends on the nature of the structure, okay, on the construction of the structure. You can see the metal has a damping factor of 0.01, but the metallic structure with joints and all, the damping actually increases and goes to somewhere between 0.03 to 0.07. it also depends on the kind of loading that it is experiences. So, like concrete structure has between 0.04 to 0.07, but same concrete structure when undergoing earthquake, it has been seen through experiment that the damping factor is somewhere between 0.01 to 0.05. So, you have to keep in mind that there are several factors that influences the damping of a system or a structure. Very often several of these dampings cannot also be modeled, and I mean some empirical understanding of the damping is developed. There are other forms of damping as well. There are Coulomb damping, hysteric damping, which we will talk about in the next lecture. In the next lecture, I will also talk about how to experimentally measure the damping factor for an underdamped system, and we will solve certain problems on the example problems on damped free vibration of single degree of freedom system. Thank you.